Unit 3, Lecture 6. This lecture carries on where Lecture 5 left off, but instead focuses on polarized turn-on snubbers, where the previous lecture mostly considered turn-off snubbing. So once again, the simple switching circuit is shown here, with a BJT, power BJT, to turn on the current to the load. But instead of having the RC snubber, which was present for turn-off, there is now in series a turn-on snubber consisting of an inductor, a resistor, and a diode. The purpose of this snubbing network is to control the current transient which will flow through the load and to the switch at turn on. So provided if this inductor is not saturated, at turn on what will happen is that this inductor will resist the change in current through the inductor, and in this way control the current throughput from the source through the load and ultimately through the switch to ground. When the circuit is switched off, any energy that remains within the inductor will discharge through the resistor and diode, which are parallel to the inductor. So analogous to the turn-off RC snubber, there will be at some point a turn-on where the switch will conduct the maximum current possible, as well as have the maximum possible voltage over the switch in one instant. This means that there is a fairly large region where a lot of energy has to be passed through the switch, and this results in the switch heating up and could possibly degrade the switch. Like the RC turn-off snubber, the turn-on snubber modulates this overlap between the current flowing and the voltage across the device terminals. So using a small inductor, there is some overlap, but it is still much better than the unaided switch, and with a large inductor, there is very little overlap, but the switching time is much longer. By increasing the series inductor, the amount of energy which is dissipated in the switch will be decreased, and the larger the inductor, the less energy will be dissipated in the switch. Of course, the larger the inductor, the longer the switching time will be. Once again, the switch loss is given by this equation, which is a half Vs, which is the supply voltage, multiplied by Im, which is the maximum current to the load. T subscript Fv is the switch time over here, where when the switch turns off, or rather turns on, the voltage falls. And then 1 over 6 multiplied by 2k minus 1, where k is given by this normalized time constant over here. Just as with the RC snubber, turn-off snubber, that there was an optimal value for the RC network in order to minimize losses in the switch, for the turn-on snubber there is an ideal value for LS which will minimize the losses in the switch at turn on. And in a similar fashion, this is a trade-off between the amount of energy which gets dissipated in the switch and the amount of energy which gets dissipated in the LR network. For the turn-on snubber, the minimum loss occurs when Ls equals 2 over 9 multiplied by Vs multiplied by T subscript Fv over Im, and this is for a value of k of about 2 over 3. A disadvantage of this type of network is that when this inductor discharges, the current discharges from the inductor to this resistor here, and this allows this voltage across the inductor to exceed the supply voltage. As mentioned, a disadvantage of this setup is that the resistor R can develop a voltage across which is larger than the total supply voltage. This can be remedied by inserting a Zener diode in place of R. Although a high voltage can still develop across the inductor when the inductor discharges, the Zener diode allows this total overvoltage to be fixed to a known value, whereas with a resistor the maximum voltage is unknown. Circuit C does away with this parallel network completely and instead places the Zener diode in a shunt configuration with a switch. In this case, energy from the inductor will be dissipated through the Zener and into ground. The disadvantage of this technique is that power is also drawn from the supply during discharge, and this means that the overall power dissipated in the Zener is higher than for the previous two cases. Finally, variation D makes use of a capacitor to form a soft clamping network. So what happens at turn-off is that the energy which is stored in the inductor moves through this diode DC and starts to charge this capacitor C. At the same time, any excess current which is not taken up by the capacitor is dissipated as heat through resistor R back towards the source. This method is advantageous when compared to the method used in C because the total amount of energy which is dissipated in the snubbing network is less than that of the energy snubbed out, or rather dissipated, using the Xeno approach. In the previous lecture it was mentioned that the turn-off snubbing circuit can be used to modulate the safe operating area of the switching device, and this is also true for turn-on networks. So the dashed line is the nominal value with k equal to 1. When k is less than 1, then the switching trajectory goes deeper into the safe operating area than before, but with k larger than 1, the switching trajectory stays below the nominal value when switching. So to summarize, or rather to reiterate, the purpose of the turn-on snubber circuit is to allow the switch collector voltage to fall to 0 while the collector current is very low. Up to now it's been assumed that the inductor being used is an air core type inductor which cannot really saturate. A saturatable inductor is an inductor with a ferrite core, and when this type of inductor is used, the switching characteristics shown here in part B can be achieved. So before the inductor has saturated, it presents a very high reactance to the change in current through the inductor, and this severely limits the amount of current which can flow. But at some point y, the inductor will start to saturate and essentially become a short, allowing all the current to flow through. The way the circuit works is that once the collective voltage Vc starts to approach 0, then the inductor starts to present less and less and less resistance to the change in current, and eventually the inductor will saturate and allow current to flow. The advantage of this is that now that the total time delay during the switch on is much shorter than for the non-saturatable air core inductor. This is possible because the inductor will now no longer limit the rate of change of current after switching has occurred. Instead, by saturating, current is allowed to immediately flow through the inductor. And to finish off, here is a circuit which includes a turn-on snubbing network as well as a turn-off snubbing network. When these types of circuits are designed, it's important to note that the amount of power which can be dissipated in the series resistor RS will have energy contributions from both the series snubbing inductor as well as the snubbing capacitor. So shown here is the equation for the amount of power which can be dissipated through this resistor RS over here. As you can see, there is a contribution both from the inductor and from the capacitor. Also of importance is that the amount of power is a strong function of the switching frequency as the switch changes from the on state to the off state. This means simply is that the faster the switch switches, the more power is going to be dissipated in this resistor RS over here. As always, there is some kind of compromise between balancing the effects of L and C when choosing R. As always, there is a compromise when deciding what value of R to use. If the R is too small, then a high switch snubber current will flow at turn on. However, if R is too large, then a large switchover voltage will occur at turn off. And this concludes this lecture. Please note that there is a small self-study section associated with this chapter in the reference text.